Welcome to Scientist, your fortnightly science from the Bioeconomy Science Institute.
Morena koutou and welcome to another episode of Scientist. Today I have the pleasure of joining you from BSI's Lincoln Plant and Food Campus, where I'm joined by Ivan Laurie, who is from the Foundation for Arable Research, and by Marlon dos Reis, who is a principal scientist with Ag Research. And today we're going to have a chat about a recent project that these folks have completed collaboratively using hyperspectral imaging and machine learning techniques to classify seeds for seed cleaning purposes. Welcome, both of you. I wondered if, to start with our podcast today, you could give us a wee bit of an overview of the why of the project. And Ivan, maybe that's one for you to lead on?
Yes, so just as a bit of a background to the New Zealand seed industry, it's a very important part of the arable production chain in New Zealand. It's actually the main export from the arable products come from our seeds. New Zealand is very highly regarded internationally as a provider of high quality seed products, both in the vegetable space and in the forage seed space. And that is currently around $300 million a year worth of exports and growing significantly. I guess the challenge for us is that a lot of the seed that we produce, we import the basic seed and then multiply it in New Zealand for re-export to the markets that originated it, especially in the Northern Hemisphere. And we also supply all the seed for the forage production of New Zealand that leads into the dairy industry and the livestock industries. So we often say that we are the engine house of the primary industries of New Zealand. So for that reason, because we trade, we import and export permanently, there is a question of maintaining that quality. But as the exports and the volumes grow, so do the challenges around doing seed testing and understanding seed cleaning. So to be able to get accurate tests on all the samples of seeds, it's very, very labor intensive. It takes a long time of very specialized people to do that work, and we don't always have them within the season to be able to meet our timelines.
Sure, I guess presumably that's a very kind of seasonally lumpy workload.
It is seasonally lumpy, and as I say, we often have to meet shipping deadlines to get that product out, or in the case where we're bringing seed into the country, we have to have it tested and approved through our own biosecurity systems to be able to get that into the ground as soon as possible. So both inwards and outwards flows are really important.
Sure, and it's super time sensitive. For the purposes of both the listeners but also myself, because I'm pretty ignorant, tell me, what are you actually looking for with seed cleaning? Is this more about seed quality, disease identification, contaminants? What are the kind of key determinants of what allows a batch in or out?
So everything that you have mentioned. So when we import seeds, those seeds have come through the appropriate channels and have already met phytosanitary requirements internationally. However, being an island nation and very protective of our biosecurity, we must keep very strict controls for biosecurity purposes. And as you know, biosecurity is a series of sieves rather than a barrier or a wall. So to try and contain any foreign material that might come in with seeds, it's really important to be as accurate as possible when we test. It's never going to be 100%, but getting to that 99% is really, really important for us in order to eliminate the possibility of weeds getting through. That's one issue, but it's also goes further. If we can improve technologies that allow us to identify purity of seed, quality of seed, viability of seed, that is also an enormous advantage to give us a head and shoulders superiority in the export markets for our quality.
Sure, so it's as much as about what's going out as about what's coming in. Yeah. And I have to admit, I'm not sure whether this was more of a FAR-led or an Ag Research BSI-led initiative, but what was, I guess, the gap that you saw in the seed cleaning process that this project set up to address?
So probably in order to explain that, I might explain the prioritization process that occurs within the Seed Industry Research Center. So the Seed Industry Research Center is a partnership between FAR that brings the levy money from the seeds that the growers bring in. It's a partnership that involves the major seed companies of New Zealand who also contribute a levy on seed sales. And it also includes the former CRIs that worked with the arable sector, which were Ag Research and Plant and Food Research, now of course BSI, as well as universities and some independent organizations like Assure Quality, who also are interested in working with us on seed testing and seed cleaning. And so as a result of that priority listing, that all the partners put on the table their needs, and some of them put their research ideas. Seed quality, seed testing is always near the top of that priority list. And so we welcome new technologies, and this was actually a conversation with the former Ag Research researchers around, here's an idea, something that we could apply, and we're really interested in that sort of new technology.
Sounds interesting. So Marlon, maybe that's a good segue for you to tell us a little bit about, at first maybe at quite a broad level, what was the project about?
So if you go to a seed testing, it's a quite fascinating process when you look at what people can do. But when we look at the requirements, for example, for weed seeds, you gotta find one weed in thousands of seeds. And that's very good when the weed seed is really different. But in those cases where the seeds is very similar to the other thousands, so it's very important to have tools that can help the expert to identify. So the motivation there was, how can we then bring tools, technology that goes on the same thing as Ivan was saying, or several civils of protection. So you have those different layers of protections. And then we look at the hyperspectral imaging. That's a very special camera, very much like the camera we have, but brings much more information. You can think this like you take an image of a drone, but then you have layers of the solid quality, moisture, and everything. So the idea of bringing hyperspectral imaging to the seeding testing process is to be able to really increase the accuracy to detect those very similar seeds, weed seeds, that what we don't want, but it's very challenging to find. So that was one of the key motivations of the project.
So hyperspectral imaging is giving you data that's over and above just morphological information about seeds, right?
Yes, so it goes beyond what you can see. It gives us information related with the chemical composition of the seeds, but also the structure. So what that means, things that are below the surface that we cannot see visually, we can pick up with the hyperspectral. And that comes back what I was saying in terms of layers of protection. So what you can see is the first layer, but that with the hyperspectral we have other layers of protection, so we can help to increase the accuracy.
So when you talk about hyperspectral imaging as capturing some chemical composition information, presumably lots of seeds are visually pretty similar looking, but they potentially have quite different chemical signatures, even if they're reasonably closely related?
Yes, and that's one of the things that we learned. For example, we learned that just the image would give us very good accuracy, but not enough to meet the criteria. But when we combine the spectral information, that's the information that translates the chemical information into something that we can use. In some cases, we achieve 100% of accuracy in very challenged systems where the seeds is very similar. So that gave us a little bit more confidence that the technology was bringing something more than what you can see.
So The idea here is partly that it gives you like a pre-filter for human visual inspection as well, though, right? Okay. And this is, again, I don't actually know much about this at all, so this is quite interesting for me. When someone is doing seed testing, presumably that's a pretty small subsample of a total seed lot. How many seeds would you typically need to inspect to feel good about saying, yeah, that's clean?
Yeah, I think in a seed lab, they are doing something over 100,000 seeds a day, because you have this sample that you collect, but that sample needs to go back to a larger sample to represent the whole batch.
Yeah, sure.
And there is several different attributes that they need to go through. With these tools, we are not replacing the people, but we're helping them to give the attention on what matters more. Because that's the challenge with seeds. There is a lots of seeds, that good seeds, but what we want to find is the one that shouldn't be there. So, and humans are really good in that process. So if you have a tool that's really efficient, so it's a better way of using the human expertise in that process.
So the ultimate idea is to have some kind of image capture system and then some underpinning model or information that you can lean on, where you can say, yes, the information we're getting from this image can definitely tell us we're looking at species X. Presumably you want to make sure that you are identifying this species, which is a sort of different question than saying, no, we don't want those ones, if that makes sense. You're not trying to necessarily say, oh, these are weeds, get rid of them. You're trying to say, no, this is definitely...
Yes.
Right.
Yeah, so with the hyperspectral image, the good side of it is that it brings a lot of information, but we gotta translate that data in something useful. And for this kind of problem, what we want is that the model, the technology identify what's known, for example, right, grass seeds, and then identify what's not supposed to be there. So we don't know what's not supposed to be there, because today the wheat seeds might be black seeds, but we don't know what's going to happen in 5 years, maybe a new type of wheat that's coming through. So the technology needs to identify the target weeds or the target seeds, and then identify, okay, this here is a weed, it's a seed that should not be there. Mm-hmm. And that's when the human expertise comes and help. So that's the filter. So you filter out everything that you know to identify something that shouldn't be there.
So with this idea that you could use hyperspectral imaging as part of the solution to this, was there any kind of pre-existing examples of this elsewhere internationally that you could draw on, or was this completely novel?
Imaging has been used for quite some time, not as much as in seed testing. Hyperspectral, there is some indications that was useful, but when we see the applications that has been described in the literature, they are comparing very different types of seeds. And the motivation here is to be able to detect, especially those seeds that are really challenged, but also be able to adapt the technology and develop the technology that can fit the needs for New Zealand, but also fits the needs for the industry. So you may have the technology applied for seed testing. That's what we call a desktop application, that you have a sample, but then when you go to a seed cleaning, for example, you have a much larger batch of seeds that you need to go through. So we gotta be able to translate the same technology for different uses that's useful for New Zealand.
So with this idea, you can take an image, you can pretty conclusively identify what species something is. How are you going from taking that image, I guess, to having a system that actually can say, yes, we can do this accurately? What's the kind of research process that's underpinned feeling like you can do that confidently for the weed seeds or the seeds that you're trying to identify?
Yes. So with this kind of technology, the technology needs to be adjusted to be able to see the seed and see what is in there. So there is a lot of parameters like the amount of light, how you shine light, that we need to find out. And that's the first step. That's what we call de-risking the technology. That's our first step to say, okay, yes, the technology works, and these are the best conditions. So the next step is how do we take these next conditions that actually can be used in the industry? Because if it's too slow, if it takes too long to do the scanning, then it might not really useful to look at large numbers of seeds. So the next step for the research is then translate the optimal settings, the optimal conditions in conditions where the industry can be used in a seed testing or seed cleaning. So in that step of the research, we worked with different types of cameras, different systems that allowed us to identify the best conditions for each use case. So then the next step after that is actually bring to the industry and do tests on the user's case.
So my personal research background is in genetics and kind of particularly within species genetic differentiation of things. And I guess something I'm curious about is I can imagine this being a more simple task telling apart very distantly related things and getting trickier kind of the more closely related they become. How much seed do you have to look at? Kind of how much has gone into building a model where you're convinced that you've got variability low enough that you can really say, well, we can pick up wheat and we know it's wheat kind of regardless of the genotype or the cultivar that we're looking at, and we're also really sure that it's not barley.
Yes, for example, in this project, we scanned more than 20,000 seeds to look at. But the number is important, but not as much important as the variation. So especially when you have seeds. So if you have a batch of seeds, they are all very similar. That's good, but that's not good for the modeling part of it.
Yeah.
So for example, we're looking at ryegrass. We want to look at ryegrass, and there is variation in those seeds. So that's where we harvest different batches, different variation, where that known seed that you're scanning has the natural variation. So as long as you are able to capture that natural variation and translate that for the models, that's a very important step, because we don't want to work with seeds that are all the same and suddenly come some new seeds that's what's supposed to be there, but because of the natural variation that was not trained, that becomes a problem. So it's very important to work very close with the industry, with people that's working with seeds, to be able to harvest that variation that helps the model.
I can imagine as well, I guess, that cultivar differences would be part of that, but presumably also growing conditions. Was this from a Canterbury field might give you a sort of subtly different answer than if you were looking at the same species, the same cultivar, even that had been grown elsewhere or in a kind of a rainier year. Did you see that kind of variation, or is it not a major issue?
Yeah, we aimed to put as much of variation, bring seeds for different parts of the country and also different years. And yes, we can learn very well those variations. But I'd say it's an important process where you have to think about all the changes that you don't expect to see in the seeds and be able to try to identify those.
Yeah, sure. So you mentioned that was very much a conversation with industry as you were going. Can you talk a little bit more about that perhaps, Ivan? What was that like from your perspective?
Yes, so we're very lucky to have a very participative group within CIRC. Of course, the farmers are a very important part of that chain because we're the main interested party that the New Zealand primary industry thrives. But all our seed industry commercial partners are happy to collaborate and to provide samples and to provide access to testing facilities for the team and to just understand the commercial realities of what's required of taking a technology like this to scale, to make it actually work in the real world. Obviously, this is just the first step. This was a proof of concept that some technology like this could be used. We were very lucky to obtain funding from the Ministry for Primary Industries SFFF fund, and very important in-kind contribution from many of our industry partners who helped out. As I say, it's really important that we now look at the follow-up on a project like this because there is, so Seed Industry Research Center is a non-profit. We don't have any aspiration to develop commercial projects or intellectual property in that sense. What we are looking at is to foster ideas like this, getting to market and then finding the appropriate partners to make it happen. So I would say that there is definitely a next stage to this project, and we're just figuring out who the appropriate partners might be to take that forward.
Where do you see the next step being for the project? If you're confident now you've got a reasonable proof of concept, what would the next step look like for you?
Yes, the whole project has been done in a research environment. We did get seeds coming from the industry representing the variation. But the next step now, as Ivan says, is to go to a commercialization partner and start and bring that technology to their routine use. And that's, I think, where we start really refine the technology to really fit the industry needs.
You've presumably had a reasonably focused start in terms of the seed that you've been trying to identify. Do you foresee extending your work so that your models are able to capture more species? Is that a focus, or are you really kind of focusing on key species for the time being?
Yes, we start with very much focused on specific applications, but we got lots of learning on the process. So with all those learnings and that we collect, we now quite confident we can move to other species or other applications as well, because all the whole methodology, the process are there. So moving to the next step is easy. Yes, there is other applications that we can see using this technology.
And I would add from a non-technology person that all of these systems seem to be moving faster than we can keep up. So the opportunity to have machine learning, artificial intelligence, which I don't understand, is becoming so much more part of the industry that we need to be able to adapt quickly to ensure that we are uptaking that technology. Otherwise, we will get left behind in an international context. And we cannot afford to do that from a New Zealand perspective, because we need to maintain our competitive advantage and be up to date with the latest technologies available.
Yeah, and I have to say, I think we're seeing that across research in BSI with some of the kind of just insanely rapid evolution in what AI can add to our research toolkit and our commercial toolkit. It's wild. Yep. Just wild to me how quickly that's moved in my own field, and I'm sure others as well. So machine learning for now, in terms of AI approaches to these kinds of questions, do you have a sense of where things could go from here?
Yeah, I think we can have very important step change in the way we do things, because AI does needs a lot of data. So there is a lot of data that AI can be trained that's non-data from literature, but you actually do need the data that's measuring the seeds on its own. When we combine the two, then we can start having a very, very strong tool, much easier to use. And align with the development of AI, as Ivan was saying, how the technology is being fast adopted by the industry, we can benefit also in terms of cost. The technology became way much more cost effective, because we knew that the way we developed the project, we work with different types of cameras to be agnostic to the technology. So what that means, we can adapt what we learn to the new devices that are much more efficient, much more cost effective for the industry. And when you connect that with AI, the tasks are becoming way much more straightforward. So using the technology is becoming way easier.
You raise an interesting point. You've mentioned a couple of times you've tried different types of cameras. Are those capturing very different types of information?
Yes, there is a balance. For example, one of the cameras that we call the top ones, that the benchmark one, it's a very good camera, but much more expensive and slower. But we have cameras that has much lower resolution, but are really, really fast. What we were able to learn is how we can use those cameras for different applications. For example, in a seeding test context, where we need really, really high accuracy, that more expensive camera is the one that makes the huge difference. But in a process where you have a large number of seeds being processed, for example, seed cleaning, then you can use a more cost-effective camera that's fast, little bit less accurate, but it still meets the criteria. So understanding what kind of technology fits better with the use case was a highlight of the project, because then it's not one size fits all. So you're not fitting a problem in a solution, but actually developing solutions that really fits with the industry needs.
And just to illustrate that, Rebecca, we've returned recently from the International Herbage Seed Group Conference in Tasmania, which was in November. So all the countries that are involved in the production of forage seeds specifically were present at that conference. And we learned there, by visiting some seed cleaning plants, that obviously there is existing technology that's already being used widespread throughout the industry, for example, for color sorting in existing seed plants. Two of the processors that we visited said that the rate at which technology is progressing is that fast for color sorting that most of the machinery that exists for sifting, blowing, vacuuming, and other ways of cleaning seeds will become redundant in a very, very short time. Because the new technologies, the imaging type based technology has become so good that all the gravity based traditional seed cleaning methods we've used for hundreds of years will disappear, all that expensive machinery.
Is there not potentially still a place for those kind of old school, lower cost techniques as a first pass method though, or would you really see them being gone?
What they are saying is that the new technology based on imaging is that good that it will probably make the process so much faster, so much cheaper, and so much more efficient than the old conventional seed dressing plants will eventually become redundant, like VCR machines or old cathode tube TVs.
And eventually being potentially very short time frames, the way we're seeing things change at the moment, I guess. It's kind of wild, isn't it? This project so far, as I understand it, has been pretty focused on weed seed contamination. Would you see the potential with hyperspectral imaging can you identify diseased seeds in this way, or seed viability, those kinds of questions?
Yes, I think these are areas of interest for us as well. And yes, there is potential to detect, for example, seed viability, the presence of diseases. And we have the experience with other applications of hyperspectral, for example, detecting bacterial spores. And that's areas, for example, we can detect whether the spore is live or dead, whether it's dormant or active. And we think those learnings from different areas can also be applied on seed, and perhaps that's one of the key advantages of the hyperspectral approach, is that you can get way much more information and then move to the other applications.
Yeah, and I suppose once you've captured the image, the data's there, right? It's then a case of what question do you ask of it, rather than having to go back and recapture it again.
It becomes a very rich resource to keep, because as you go, more data you collect. And that's what's happening. You're collecting the hyperspectral, but there is other flows of information that's became much more common now, so you can correlate the two and start in new applications.
An interesting kind of extension of what I feel like are scientists' natural hoarding tendencies too, this kind of staggering amount of data that we can hold on to now and ask questions of much later. The most recent podcast I recorded was with Pierre Rodier, who's a soil scientist at Manaaki Whenua, and we talked a little bit in that about the ability they have to go back to these very old literal physical collections of soil and ask questions of them. And I guess I don't know quite how you imagine using digital imagery in the same way, but we don't always know now what questions we can ask with the data that we have, or what we might want to ask of it much later too. I just think I guess it's an interesting question. How do we look after these data resources once we've collected them too?
Yes.
We're lucky that there are very good collections of seed in New Zealand, historical collections of pure seed. As you know, we've got a gene bank here at Lincoln, but there's also a very important resource at the Margot Ford Centre in the North Island. All of those historical seed banks can help us also look back at historical data, and the fact that we've got such an active industry and such an amount of different species. I mean, the arable industry deals today in easily over 50, 60 different species that we produce and export to the world. That provides a very rich resource for samples and data for our industry. I think the other element that's really important here is that the way in which we store and capture that data is changing day to day, and that makes what used to be very protective and personal a lot more publicly available, because the technology is making that possible. So we're optimistic. We think that a combination of these new technologies, but as you say, there might be other equipment that is still required to work in conjunction, will make that easier. But as Marlon correctly said, we're not looking here to replace the human element. It's just making those tasks faster, more efficient, and just adapted to the new realities. We also work in a framework where imports and exports of seeds are regulated by protocols. So ISTA, which is the International Seed Testing Association, have their own protocols which are recognized by multiple different trading countries. Well, those protocols might change as the realities of technology change and new things can be incorporated.
Yeah, and I guess the ability to keep up with those changing regulations, but also, as you said at the start, there's that set of things you need to meet, and then there's what we choose to do as a country or as an industry over top of that for our kind of own peace of mind.
And biosecurity too, I mean, that continues to be key. That is a point of difference that New Zealand does have and that we have to try and protect as much as possible. So you were saying the ability to perhaps detect diseased seeds or seeds that have been attacked by pests that could possibly be present in the sample, that kind of alert system would contribute enormously to maintaining a pest-free environment to grow our seeds in.
Yeah, the potential for that for early warning, I guess, is pretty staggering, isn't it? I want to go back for just 2 seconds to something you just said. 60 species at least.
Yep, that's how much we trade in. I mean, everything, if you think of the range of vegetable seeds alone that are produced in New Zealand, and that includes everything from pak choi to carrot seed, which we produce about 50% of the world's carrot seed. We produce about 40% of the world's radish seed. We're the world leaders in clover seed, white clover seed production. We've probably got the lion's share of ryegrass seed production, not only for export but for domestic use. You look through that range, and then if you think of all the different species that coexist within those categories, it's a huge range, and we're going further. I mean, we produce oil seeds, we produce seeds for pharmaceutical purposes. The list gets longer.
The engine indeed. I perhaps naively didn't realise until I moved to Canterbury, I guess 8 or so years ago now, how big an industry the seed industry was for New Zealand. It still kind of blows my mind that you just don't typically hear about it as a... And I work for an agricultural research institute, and I still didn't really appreciate until I moved here quite how big an industry it was. It's pretty cool.
Yeah, and the reason for that is because a lot of what we produce in the arable industry, I wouldn't say loses identity, but becomes either an ingredient or becomes a plant that grows out of the seeds that we produce. So that it's not always immediately identified by the consumer. But somebody had worked it out. I think Nick Pike back at FAR a few years ago had worked out a figure of how many carrots consumed in the world every day came from a seed that had been grown in New Zealand originally, even if the carrot itself had been grown in Europe or America or in Asia. And those calculations are really staggering when you see the influence of what just a seed can have on the subsequent production of food or milk or meat.
Yeah, producing it, well, not producing it, kind of processing it one step further via a cow or something. Yeah, staggering numbers, I think. This is fascinating. Thank you both so much for this chat. Before we wrap up, I guess, are there any other kind of messages that you would have liked to have shared that I've perhaps not touched on?
From our behalf, we're very grateful to the team at Ag Research, now BSI, who conducted the project efficiently, on time, delivered the results and the reports, which is fantastic. I would also like to thank the industry partners who contributed not only financially but in kind and with their time to support the project, and to the Ministry for Primary Industries for providing a large portion of the funding for this as well. And my message is, if anybody is interested in taking this technology further, either contact myself at the Seed Industry Research Center or at FAR, or contact Ag Research and express your interest in what we can do for the next steps to take this to a commercial reality.
Collaborators welcome then. It sounds like a really nice example, I think, as BSI often is, of combining a lot of different kinds of expertise. You know, you've got modelling, you've got imaging, you've got biologists, kind of seed biology in there, but also that thing that I think we do really well of being pretty well connected with industry and leaning pretty well on our commercial partners to kind of maximize what we actually learn along the way and make sure it's useful. This is very cool stuff, and I would look forward to hearing more about it soon, I hope. Thank you both so much for your time today. And thank you, of course, to our listeners for listening to another episode of Scientist. We always really appreciate if you can like or rate our podcasts. Helps us get them out there a little bit further. Until next time, mā te wā.